8.3, Example 2. Before we dive into Example 2, I want to talk about how to generalize rates of growth for different functions. So we're going to show, for part A, that a to the x when a is greater than 1 grows faster than x squared as x approaches infinity. So remember, a to the x could be 2 to the x, 3 to the x, e to the x, any exponential function where a is greater than 1. So in order to do this, we let the limit as x approaches infinity, and I want to show it grows faster, so I'm going to put it in the numerator and divide it by x squared, representing our polynomial. So when I plug that in, I get infinity over infinity, so I'm going to need to use L'Hopital's rule. And again, the derivative of any exponential is a to the x times ln of a divided by 2x. Again, when I plug in infinity, I'm going to get infinity over infinity. So we use L'Hopital's rule yet again, and I get a to the x times ln of a times ln of a divided by 2. Now keep in mind, ln of a is just a number. So I'm going to do the limit as x approaches infinity of a to the x times ln of a squared over 2. The only x I have is right here. So a to the infinity would just be infinity. So I get infinity. And that's what I wanted. I wanted to show that when I plug in infinity, I'm going to get infinity to show a to the x grows faster. Okay, for part B, I want to show that 2 to the x grows slower than 3 to the x. So if this is true, I better get 0 as my result. And if I want it to be slower, that means I still put it in the numerator. So I get this is the limit as x approaches infinity of 2 to the x divided by 3 to the x. Now we're going to need here some fancy algebra. So I get this is the limit as x approaches infinity, 2 over 3 to the x power. That's bringing out the x. And from our knowledge of limits, since the absolute value of 2/3 is less than 1, we get that when we plug in infinity, we get 0. And that's just from the knowledge that if you have a fraction that's less than 1 and you raise it to the infinite power, you end up getting 0. What might help is to actually check out the graph of this, which we'll do right now. So you'll notice when a is less than 1, the end behavior goes to 0. And as this thing starts to grow, you'll notice it's going to flatline. And once it becomes larger than 1, the end behavior will shoot towards infinity. So once that 0.8 goes to 1.1, you'll see this is going to start to grow up. And if I zoom out, you'll see how it grows once it's larger than 1. For part C, I want to show that if a is larger than b, which they're both bigger than 1, a to the x grows faster than b to the x. So what we're going to do is we're going to go ahead and take our limit as x approaches infinity of a to the x divided by b to the x, because I want to show a grows faster. So this is the limit as x approaches infinity of a divided by b to the x power. And notice that a divided by b is greater than 1 because a is bigger than b. So if a is 5, b has to be like 6 or something, or 6.1. So once it becomes larger than 1, we know that this limit goes to infinity. Therefore, a to the x grows faster than b to the x. Example 2. We want to show that ln of x grows slower than just x. Okay, so we go ahead and set it up with our limit as x goes to infinity. And if I want to show ln of x grows slower, I do ln of x divided by x, and hoping that I'm going to end up getting 0. So when I plug that in, I get infinity over infinity, which is no good. So we're going to use L'Hopital's rule. And I get the limit as x approaches infinity. The derivative of ln of x is 1 over x, divided by the derivative of x is 1. So this becomes the limit as x approaches infinity of 1 over x. And then when you plug in infinity, you end up getting 0, because 1 over infinity is 0. So therefore, we have ln of x grows slower than x. For part B, I also want to show that ln of x grows slower than x squared. Really what we're doing here is showing that it grows slower than any powered polynomial. So its limit as x approaches infinity of ln of x divided by x squared. Again, when you plug that in, we're going to get infinity over infinity. So we're going to need L'Hopital's rule. So we get the limit as x approaches infinity, 1 over x divided by 2x. So this is going to be the limit as x goes to infinity of 1 over x times 1 over 2x, because you're going to multiply by the reciprocal. So you get 1 over 2x squared. So we take the limit as x approaches infinity of 1 over 2x squared, which is 0. Therefore, ln of x grows slower than x squared. Okay, on your own, I want you to try to show that ln of x grows slower than x minus ln of x. This one's a little trickier. Same process, though. So go ahead on your own and try that out. All right, so let's give it a try. So we're going to do the limit as x approaches infinity. And I want to show this grows slower. So it's going to go in the numerator than this. Now, when you plug in infinity, it really becomes infinity minus infinity in the denominator. But using end behavior models, you know that x is the end behavior. So it's just infinity. So that's no good. We're going to need L'Hopital's rule. So we go ahead and get L'Hopital's rule out. Take the limit. X approaches infinity. The derivative of ln of x is 1 over x divided by 1 minus 1 over x. And this is where just your fancy algebra comes in. So this is the limit as x approaches infinity of 1 over x divided by x over x minus 1 over x. I'm trying to find those common denominators. So this is the limit as x approaches infinity, 1 over x divided by x minus 1 over x. So now I've got fractions within fractions, so that's no good. So it's 1 over x times x over x minus 1, multiplying by the reciprocal. This is going to reduce off. And we get this is the limit as x approaches infinity of 1 over x minus 1. Then once you plug in infinity, you get 1 over infinity, which is 0. So therefore, ln of x grows slower than x ln of x.